In this video, we're going to learn how to calculate frictional losses in piping systems. So in the last video, we introduced this topic very briefly, but here we're going to look at the details of how to calculate that head loss term. So we're beginning here with Bernoulli's equation written with losses. So remember, the basic Bernoulli's equation is just those three terms plus these three terms. So the frictionless form of Bernoulli's equation is the sum of those three terms is a constant. Now notice here I've written this in pressure form. So the units of each term in Bernoulli's equation written like this are pascals. In the previous video we had the same equation, it was just divided by rho g, so it was in head form. Now when we write it in pressure form like this, we call the losses delta PL. So we call this head losses in the previous video. Here we're going to call it pressure losses. But realize those are exactly the same things. They're frictional effects that reduce the energy in the system as we go down the pipeline. Now, we also introduced in the last video that these pressure losses are broken up into two contributions. So the total pressure losses, delta P losses, is made up of a frictional loss term, so pipe friction this is, and then so-called minor losses. Now realize both of these things are due to friction. We just tend to call the pipe friction part frictional losses and the part associated with fittings minor losses. So we're going to take a look at how to calculate minor losses in piping systems first, and then after that we'll go back and learn about how to calculate pipe friction. So first of all, minor losses are calculated by two different techniques. Now the first one that I'm going to show here is by far the most common, but the second technique we also need to know about. So this first technique makes use of something called a minor loss coefficient. So the Km on the right hand side of this equation is the minor loss coefficient. Now we could be calculating minor pressure losses, delta Pm, or if we're working with Bernoulli's equation in head form, we would be calculating minor head losses, Hm. Well, realize the minor loss coefficient that we use in those two cases is exactly the same. It's exactly the same number. So once we've determined a minor loss coefficient for a particular fitting, we can use it to calculate the pressure loss or the head loss, whichever one is appropriate for the calculations that we happen to be doing. Now, what do we do with that minor loss coefficient? Well, in order to get the pressure loss due to flow through a particular fitting, you would look up the minor loss coefficient for that fitting, and you would multiply it by rho v squared over 2 if you were working in terms of pressure. If you were working in terms of head, you would take that same number and multiply by v squared over 2g. Now, a very important thing to realize about applying minor loss coefficients to get head losses or pressure losses is you need to know what velocity to use in this equation. Now, if you're looking at a fitting where the inlet and exit diameter is the same, that means the inlet and exit velocities are the same, and there isn't really any ambiguity here, you would just use that velocity. But let's say you were looking at a fitting like the one we saw in the last video, a contraction, where the inlet and the exit velocities were very different. Well, which one would you use in this equation? Well, you need to look at the place you got this minor loss coefficient from, because that needs to specify which velocity you should use in these equations, the inlet or the exit velocity. So all of the sources of minor loss coefficients that we're going to look at, somewhere in those sources there'll be a note or like a footnote or an explanation somewhere saying which velocity you need to use when you use that minor loss coefficient to calculate a minor pressure loss or a head loss. So that's something to keep in mind. So in the next slide, we'll go ahead and look at where these minor loss coefficients come from. But before we do that, we need to look at the second way that we might be calculating minor pressure or head losses. and that is through the use of an equivalent length. Now, the way equivalent length works is it essentially is saying that if you were to replace this particular fitting with a particular length of straight pipe, the same as the fitting is connected to, then that length of straight pipe would have the same pressure losses through it as the actual fitting. So that's what's meant by an equivalent length. So in this equation, that equivalent length is LEQ, and we just apply that LEQ as if the pipe were a little bit longer than it actually is. So when we look at how to calculate frictional losses in pipes, you'll see that we calculate them from FL over D, rho V squared over 2. We'll be talking lots about where this F comes from. It's called a friction factor. But if we're using the equivalent length technique, then when we're calculating the frictional losses in the pipe, we would just add on a little bit to the length. So we would just pretend that the pipe's a little bit longer than it actually is to account for the frictional losses in any fittings that are along the way. Now, like I say, 90% of the time, minor losses are accounted for by these minor loss coefficients. But sometimes you will run into this equivalent length concept to calculate minor losses. In one of the labs that you're going to do in the course, you calculate minor losses using both of those techniques. So watch for those techniques when you're doing that lab, the pipe flow lab. It's the second last lab, so it'd be lab 4. Okay? Now, where does all this information come from? Where do we get these minor loss coefficients? Well, when you're working in industry, you will get these minor loss coefficients from the manufacturers of the fittings. So there'll be catalogs or online resources you can look at. So for different types of elbows and T's and valves, the minor loss coefficients will be specified in the technical data for those fittings. Now, as I said, somewhere in that technical data, it also needs to tell you what velocity those minor loss coefficients are based on, because you need to know what velocity to put in these equations when you calculate that minor loss. So in practice, this information comes from technical data produced by manufacturers of these fittings. Now, for our purposes, there is a set of tables in our textbook that we're going to use for minor loss coefficients. So I'm just going to summarize the resources in our textbook and what types of fittings they have minor loss coefficient information for. Well, table 6.5 is probably the one that we use the most because it has minor loss coefficients for valves, elbows, and T's. So these are not any particular manufacturer's valves, elbows, and T's, but they're just generic numbers for different designs of valves, elbows, and T's. And if you look at table 6.5, you'll sort of see the variety of different types of elbows and T's that are in there. But that's where we're going to go for our minor loss coefficient information. There's several figures in Chapter 6 that also give minor loss coefficient information. For partially open valves, figure 6.18 should be used. So notice figure 6.5 also has valves, but that's for fully open valves. Well, if you have a valve that is partially open, the minor loss coefficient is going to be a lot bigger. So figure 6.18 allows you to get minor loss coefficients for valves that are partially open. 6.20 is for bends. Now again, table 6.5 has minor loss coefficients for T's, but a T is different than a bend. A T is a separate fitting that is either a flanged or a screwed or perhaps a soldered or welded connection to the pipes, whereas a bend is not actually a separate fitting, it's a bend put in the pipe. But those bends do increase the losses a little bit over what they would be if that same chunk of pipe were straight. So we add that extra loss in through a minor loss coefficient. 6.21 is entrances. So if we go from a large reservoir into a pipe, there's a frictional loss associated with that, and that's accounted for in these calculations by a minor loss coefficient. Figure 622 has expansions and contractions. So that's when we go from one size of pipe to another size with a sudden expansion or a sudden contraction. And finally, figure 623 shows gradual expansions. So that's kind of similar to the fitting that we saw in the last video when we were learning about hydraulic and energy grade lines. That was actually a gradual contraction, but if the flow was going through the other direction, it would be a gradual expansion. So we have quite a few resources in our textbook that will allow us to look up minor loss coefficients for various types of generic fittings. But of course, in practice, we would use actual manufacturer's data to come up with these values. Now, the other scenario that you might be faced with is you're working for a company that is actually producing or manufacturing fittings. Maybe they're manufacturing valves or elbows or T's. And your task as an engineer might be to figure out what the minor loss coefficient is. So you might be the one actually writing these catalogs that I'm telling you to go look at. Well, the way you would do that is you would do it experimentally. You would pump fluid through your new valve, you would measure the pressure drop, and you would calculate what the minor loss coefficient is, and then you'd put that number in the technical data so that somebody that purchases that particular valve or fitting knows what the losses are going to be when they pump fluid through it. So that's where minor loss coefficient information comes from. It's experimentally determined. So that's the minor loss coefficient. Now I should say a little bit about the name minor loss coefficients. Why is it called that? Is it not very important? Well, in many piping systems, that in fact is the case. The minor losses tend to be a very small part of the total pressure losses. And the pipe friction that we're going to look at next dominates. It's much more important. So in a case where we have long straight runs of pipe and relatively few fittings, that will certainly be the case. Minor loss coefficients will be very, very small compared to pipe friction. So that's sort of where they got the name minor losses from. Now, there certainly could be piping systems where the runs of straight pipe are relatively short and there's a lot of fittings. And in cases like that, the minor losses could actually be very substantial. In fact, they might even be bigger than the pipe friction. But in general, for most systems, they're quite small compared to the pipe friction. So that's our look at minor losses in piping systems. In the next video, we're going to take a look at the second and most important contribution to pressure losses in piping systems, and that's pipe friction. See you then.